Real analysis is the study of real numbers and functions of real numbers. As such, the first step in this subject is actually defining what the real numbers are. In this video, I hope to explain where the reals come from, as well as why we need them. The most obvious set of numbers is the natural numbers, also called the counting numbers, which are just your standard 0, 1, 2, 3, and so on. However, axiomatically the natural numbers can be defined as follows. 0 is a natural number, and every natural number has a successor. These axioms make clear two important properties of the naturals. They are an infinite set, meaning there is an infinite number of natural numbers, and n has no upper bound, meaning there is no biggest natural number. Because the naturals were defined using successors, n is an ordered set, and so its elements can be plotted on a line. This gives a nice geometric definition of addition, where arrows from 0 to the numbers are lined up tip to tail, and because n has no upper bound, addition always results in a number in n. Here we say n is closed under addition. Subtraction can be given the geometric meaning of reversing the direction of one of the arrows and lining them up tip to tail. However, it is not hard to imagine a situation where this results in a number not in n. To fix this, we extend n by introducing the negative numbers. This new set is called the integers, aka the whole numbers. We can loosely define the integers as a set containing all the elements in n, and for any integer x, there is a unique integer such that their sum is 0. We call this unique integer the negation of x. We can put an order on z using the order on n by stating that if x is less than y, then minus x is greater than minus y. This allows us to extend the number line. Notice where n had no upper bound, z lacks an upper and a lower bound, meaning it has no smallest or biggest number. Multiplication of two numbers can be defined as repeated addition and is closed in z. However, division, defined as the inverse of multiplication, is not closed. The solution to this is to add a number for every combination of one integer divided by another. This defines the rational numbers q. Q effectively fills in the space between the integers. A sequence is a set where each element in the set has an index in the naturals, so we can put the elements in order of their index. An infinite sequence is a sequence with infinitely many elements, so the index runs through all the natural numbers. A sequence is bounded if there is a number smaller than any number in the sequence and another number larger than any number in the sequence. If a sequence in Z is bounded and infinite, then the sequence must start to repeat numbers because there is only a finite number of numbers between the lower and upper bounds. However, in Q, there is an infinite number of elements in any interval, so a bounded infinite sequence in Q can avoid repeating the same numbers. An example of this is the sequence 1 over 1 plus k. This sequence is bounded above by 1 and below by 0. As you can see, each element is less than the previous. In more formal language, the sequence is monotonically decreasing, and so the elements are approaching the lower bound 0. However, the sequence never actually reaches 0, and it's fair to ask, is 0 what the sequence is approaching, or is it something else very close to it? We can prove that the sequence is approaching 0 by showing that for any distance from 0, denoted epsilon, after a certain number of terms in the sequence, the remaining terms stay within epsilon distance of 0. This proves the sequence tends to 0, because if it tended to a different point, we could set epsilon to be less than the distance from that point to 0, and so the terms couldn't stay within epsilon of 0 while tending to that point. 0 is called the limit of the sequence, and the sequence is said to converge to 0. A way you might visualize the limit is that no matter how much you zoom into that point, while you might lose the earlier terms, the rest of the sequence will continue within that frame. For a strict definition of convergence, a sequence AK is said to be convergent if there is a point, let's call it A, so that for any neighborhood of A, past a certain index k, the sequence remains within that neighborhood, then A is called the limit of that sequence. Now let's consider this sequence, defined recursively so that the next element is calculated using the previous one. Writing out the first few elements and plotting the sequence, we can see that the terms rapidly hone in where A2 is, so much so that they're all drawn on top of each other. If we zoom in on A2, we see there is some separation between it and the rest of the sequence, and if we zoom in on A3, we see the same thing. We would also see this if we were to zoom in on the points in the previous sequence, but if we were to zoom in on the limit point, 0, we would always see the sequence continuing within that zoomed frame, because the sequence is converging there. In this sequence, however, there is no element in Q that is a limit. This is because the sequence is tending towards the square root of 2, which is not a rational number. Despite the fact that the sequence isn't convergent, its elements are getting closer together. We call such a sequence a Cauchy sequence. We can write the definition of a Cauchy sequence by taking the definition of a convergent sequence and replacing the limit a with any an where n is also greater than or equal to some minimum index. Comparing the definitions of convergent and Cauchy sequences, we can see that any convergent sequence is also Cauchy because we can take any two elements within half epsilon of the limit, and those elements must be within epsilon of each other. If the converse is also true, i.e. every Cauchy sequence has a limit it converges to, then the space is called complete. As the previous sequence showed, Q is not complete. We wish to define the real numbers as an extension of Q that forms a complete set. Finally, we've come to defining the real numbers. There are several different ways to do this, so if this particular process doesn't make much sense to you, maybe consider looking at some of the other approaches that exist. They are all equivalent, but often emphasize different properties of the reals. Here we define the real numbers as follows. The elements of R are Cauchy sequences in Q. Two Cauchy sequences are equivalent if their difference tends to 0. R has an order to it. One element is greater than or equal to another element, if and only if they are equivalent, or, after some index, each element of one sequence is greater than the corresponding element in another. And addition and multiplication of real numbers yields a new real number, where each term in the sequence is the sum or product of the elements of the sequences of the reals being added or multiplied. Taking a closer look at these statements, we can see from the first one that Q is a subset of R by associating every rational number in Q with a sequence of just that number in R, noting that a sequence that repeats the same number is Cauchy. The second statement relates to the fact that elements in R are not unique. An example of this is a sequence of just ones and the sequence of 0.9 repeating. Because the difference between these two tends to 0, we get the result that 0.9 repeating equals 1. The third statement just defines an order on R. It is worth noting that if x is greater than y in Q, then the corresponding point for x in R is greater than the corresponding point for y, and so the order in Q is preserved by this definition. And the fourth statement is just the definition for addition and multiplication for elements in R. Having these definitions does give a nice way to write the condition for two elements in R to be equivalent. We wrap this up by discussing some of the properties of the real numbers. The first is that R is indeed complete. This is shown by the fact that R has the least upper bound property, which states that for any subset of R with an upper bound, there is a smallest upper bound. The proof of this is as follows. Let S be a non-empty subset of R. If S has an upper bound, we can take a U0 that is an upper bound on S and an L0 that is not an upper bound on S. Furthermore, we can take U0 and L0 to be rational. Now if we take the point in the middle of U0 and L0, we can assign that point U1 if it is also an upper bound on S, and let L1 equal L0. Otherwise, we set L1 as the midpoint and let U1 equal U0. By repeating this using the newest terms in the sequences, we obtain two Cauchy sequences, U and L. Note that U and L are Cauchy sequences of rational numbers, and so U and L are in R. Now notice that the difference between the terms in U and L halves each term, and so the difference between these two sequences tends to 0, making U and L equivalent. Any x greater than U is greater than some upper bound in U, and so x is also an upper bound. Likewise, any x less than U is less than some not upper bound in L, and so x is not an upper bound. Therefore, U is a least upper bound on S, and so R has the least upper bound property. Lastly, we can see that Q is dense in R, meaning that any number in R can be approached using a sequence in Q. This comes from the definition of elements of R as Cauchy sequences in Q. This is important because it means that R is the smallest extension of Q that is complete, because if we remove any element in R, then there is a Cauchy sequence in Q that isn't convergent. This concludes the construction of the reals and some of their basic properties. In the next video I plan to go over normed, metric, and topological sets, as well as how these apply to the real numbers. I hope to see you there. Thank you for watching.